Welcome to the training module on Hall effect-based current sensors. This training module introduces basic knowledge of Hall effect sensors and Allegra's ACS current sensor IC family. The basic Hall element is a small sheet of semiconductor material. A constant voltage source will force a constant bias current to flow in the semiconductor sheet. The output will take the form of a voltage measured across the width of the sheet that will have negligible value in the absence of a magnetic field. If the biased Hall current is placed in a magnetic field with flux lines at right angles to the Hall current, the voltage output is directly proportional to the strength of the magnetic field. This is the Hall effect discovered by Edwin Hall in 1879. All Hall effect devices are activated by a magnetic field. Magnetic fields have two important characteristics: flux density and polarity. To operate the Hall devices, the magnetic flux lines must be perpendicular to this face of the package and must have the correct polarity. The Hall element is a basic magnetic field sensor. The output voltage of the basic Hall element is quite small. This can present problems, especially in electrically noisy environments. Therefore, it requires signal conditioning to make the output usable for most applications. Addition of a stable, high-quality DC amplifier and voltage regulator to the circuit improves the transducer's output and allows it to operate over a wide range of supply voltages. This Hall effect sensor IC provides an easy-to-use analog output that is linear and proportional to the applied magnetic flux density. The addition of a Schmitt trigger threshold detector with built-in hysteresis and an open collector NPN output transistor, as shown in the right figure, gives the Hall effect circuit digital output capabilities. As systems extend and expand the exploitation of the latest power semiconductors, examples IGBTs, MCTs, etc., that manifest a very relentless advance in power output limits, a prerequisite demand for sensing these escalating current levels is increasingly apparent. Hall effect ICs provide non-intrusive current sensing techniques and safe, isolated detection of high current levels without dissipating the sizable amounts of wasted power associated with resistive current sensing methods. Further, Hall effect current sensing provides electrical isolation between the current carrying conductors, hence a safe environment for circuitry, operators, etc. The central element of all Allegro current sensor ICs is a precision, linear, Hall effect-based magnetic field sensing circuit. For standard models, the circuit is bidirectional, as shown in the figures, allowing current to flow in either direction. The magnetic field generated by the current is sensed by the integrated Hall IC and converted into a proportional voltage. The Hall effect sensor IC detects the motion, position, or change in field strength of an electromagnet, a permanent magnet, or a ferromagnetic material with an applied magnetic bias. Energy consumption is very low. The proliferating current sensing applications for Hall effect sensors become even more diverse, plus expand and grow as other designers endeavors to protect systems, create more reliable, bulletproof environments, equipment, and reconcile any safety issues. Here we list the prime applications of cost-effective Hall effect sensors for current sensing. For small nominal currents up to plus and minus 20 amps, the ACS 71X families of Hall effect-based electrical current sensor ICs are packaged in a standard footprint SOIC 8 surface mount package. They measure current by sensing the magnetic field it generates as it passes adjacent to the Hall element. They measure this field directly without the use of a magnetic concentrator. The lack of a concentrator has the advantage of nearly eliminating magnetic hysteresis as a source of error in the IC. However, this also leaves the ACS71X devices less shielded from external magnetic fields that could distort the current measurement. For higher currents, the cross-section of the copper conductor has to be increased to accommodate the current density within the material, which is provided in the CB or CA package. Because of the magnetic coupling between the thicker conductor and the linear Hall element, a flux concentrator has to be used. The thickness of the copper conductor allows survival of the device at higher overcurrent conditions. Through careful design of the system, the primary conductor resistance is typically as low as 100 microohms, and a minimum RMS isolation voltage of 3 kV is achieved between the primary path and signal sides. A block diagram is shown in the figure. The magnetic flux generated by the primary current affects the Hall element. A bi-CMOS chopper stabilization circuit is utilized to reduce signal offset and to stabilize the output of the IC over its operating temperature range. The on-chip electronics produces an analog voltage that is proportional to the input current. The ICs are designed to measure both positive and negative currents. Chopper stabilization is an innovative circuit technique that is used to minimize the offset voltage of a Hall effect element and an associated on-chip amplifier. Allegro patented a chopper stabilization technique that nearly eliminates Hall IC output drift and induced by temperature or package stress effects. This offset reduction technique is based on a signal modulation-demodulation process. Modulation is used to separate the undesired DC offset signal from the magnetically induced signal in the frequency domain. Then, using a low-pass filter, the modulated DC offset is suppressed while the magnetically induced signal passes through the filter. The anti-aliasing filter prevents aliasing from happening in applications with high-frequency signal components, which are beyond the user's frequency range of interest. Smart battery systems require circuitry to monitor cell voltages, temperatures, and currents. The most difficult to design in properly is current measurement. The reasons for this are the requirements for accuracy, power dissipation, and solution size. By using a Hall effect device as a shunt solution in the battery pack, the power dissipation in the pack can be reduced. The advantages of using Hall effect devices is readily apparent with the low insertion loss of the device. The use of a Hall effect device, as shown in the figure, can increase the accuracy of current measurements. This block diagram shows a high current path and a low current path. The low current path can be enabled for better accuracy at monitoring small currents. UPS solutions require using the line voltage to charge a battery that is used to supply line voltage for a system in the event of power failure. The goal of the UPS is to supply as much energy as possible with the maximum efficiency. The ACS series Hall effect devices are ideal for monitoring the input power or battery charge current for several reasons. The obvious benefit for a small form factor Hall effect solution is that the volume required is a fraction of the equivalent current transformer solution. And in addition, there's an elimination of gain and additional protection components.